Hi everybody. I hope you're enjoying Shakespeare. We're going to be talking today about motion vectors. And so I want to review a little bit about what we said yesterday. Yesterday we allowed a vector A to be represented in terms of its components in this way. And the picture is that we have unit vectors I and J, both of which are of length 1 and are perpendicular to one another. And so the vector AXI plus AYJ will stretch I by the amount AX, and it will stretch J by the amount AY, and add the two together, so that AXI plus AYJ is going to end up being this vector. And we noted that there are two common notations for vectors. One will represent it as I have it red here. The other, which you are familiar with from the regular physics class, will represent the components in angle brackets like so. These two are two ways of writing the exact same thing, but here we are omitting the I and J unit vectors. For a lot of the work that we're going to do, I'm going to retain these unit vectors here because they're going to emphasize that we have a linear combination of the vectors I and J. Today I want to consider what happens if we have a position that is going to be defined parametrically by x of ti plus y of t j. What does this mean? Well, our position vector is going to measure the distance from the position of the particle to the origin. So if I place my origin right here, and I watch the particle's path as it moves along the parametric curve, then at any time, the position vector is going to be the vector that takes me from the origin to the point x, y along the curve. And since x and y are functions of t, then the position vector is legitimately a function of t as well. So watch what happens as time goes on. If my starting t puts my particle right here, then the initial position, r0, would be right here. And now as the particle moves along, r is going to change. So this might be r1, r2, r3, and so on. So the question now is, how are we going to measure the various quantities that we're interested in with regard to motion? What does it mean, for example, to have a displacement, delta r? Delta r is going to be equal to a final minus an initial. And so if I go over to my curve right here, and I pick one point, say R3 here, to be the final, and one to be the initial, then the delta R is going to be the vector that is the difference between those two. It is the vector that takes me from the initial to the final. And remember that vector subtraction is carried out by placing the vectors tail to tail and connecting, and all of my position vectors automatically have their tails at the origin. So that's very convenient. Here comes my delta R. So notice that what delta R is really doing is it is tracing out a path that goes straight across rather than along the curve. So we would consider that displacement to be the total change in position as we go from R initial to R final. If I want to leverage that displacement to give me a measure of initial or of average velocity, then my average velocity, the average, is going to be a vector that is delta r divided by delta t. I want you to notice very carefully what's happening here. We're taking a displacement vector and we are dividing it by a scalar value, delta t, the amount of time that it takes to get from initial to final. Just to be clear about this, we would write this in the form of a scalar 1 over delta t times delta r. In other words, I'm taking the delta r vector and I'm stretching it by a factor 1 over delta t. If delta t is very large, say a year, then my delta r is going to be contracted, so that my average velocity would be a very small vector, like so. Let me copy this down. So here's our delta r. And if I have a large delta t, large amount of time, then my average velocity is going to point in the direction of r, but be much smaller. If, on the other hand, delta t is very small, maybe a millisecond, then my average velocity is going to end up being very large, but still is going to point in the direction of delta r. So this is v average for a small delta t. It's going to be the average for a large delta t. The average velocity will always point in the direction of delta r and never backwards, because my delta t from initial to final is always a positive value. I mean, I could do it backwards, but that wouldn't be very useful or interesting. Now, what if I want to take my average and make it instantaneous? In other words, how does the calculus work here? Let's do a picture, and then let's come back and do it analytically with our r is specified up here. So the instantaneous velocity then is going to be the vector that is the limit as delta t goes to 0 of delta r over delta t. And graphically, along the curve here, if I pick a point t and I go out a small time frame, delta t, like so, so that I get a very small delta r, like so, and now I divide by the delta t, giving me a much larger average velocity like that, the instantaneous velocity is going to be the limiting case of that process of taking the delta r and dividing by very small delta t's. And you can see that when we do that, we're going to end up with a vector that is graphically is going to be tangent to the curve at this point. Now, let's come back and do this analytically so we can put some more definition on it. If I take my r of t is equal to x of ti plus y of tj, and I replace delta r with x of t plus delta t I plus y of t plus delta t j minus x of t I plus y of t j. And all of that divided by delta t. Notice that what we have here, this fairly large expression represents r of t plus delta t. And this expression right here, of course, is r of t. But now we can just do some algebraic rearrangement using properties of vectors. Because first of all, we have two different um, components that are multiplied by the vector I, and so I can group those together. And we have two different components that are multiplied by j, so that I can group those together as well, and divide by delta t, like so. But now I can use linearity to write this as the limit as delta t goes to 0 of x of t plus delta t minus x of t all over delta t times I plus the limit as delta t goes to 0 of y of t plus delta t minus y of t all over delta t times j. Now we examine the quantities on the inside right here, and we can see that this guy is nothing more than dx dt times I plus dy dt times j. In other words, we were able to differentiate our vector quantity simply by walking down term by term. Let's write it like this, that the derivative x of ti plus y of tj, which is my velocity vector, my instantaneous velocity vector, is nothing more than the derivative of x I plus the derivative of y j, just like that. We can differentiate component by component. And if you think about it in terms of derivative rules, this also makes a whole lot of sense, because the derivative of a sum should be the sum of derivatives. And each of the vectors I and j are constant in the sense that they do not change in either magnitude or direction. I remains in the direction of the positive x-axis with a length of 1. J remains in the positive direction of positive y-axis with length 1. And so I can bring that out of my derivative using constant multiple rule, essentially. Here I'm extending the constant multiple rule. What justifies that mathematically is the limit that I showed above. And so that gives me x prime of t times I plus y prime of t times j. So we have two different ways to get to the same result. We can either use the limit definition of derivative to show that the derivative of r is going to be the derivative of each component separately, or we can use derivative rules and extend them to get the derivative of r is equal to the derivative of each component separately. And so we like that. Now before we do some more with this, let's get an example going here. And for our example, I'd like to choose this curve right here. And here we have our position vector r is equal to blah, blah, blah. Let's observe some things about this. First of all, the position, because the vector is a function of time t, is going to define a parametric curve. I can take this position vector as a function of t and split into components so that x of t is 3 cosine of t over 2, and y of t is equal to 3 sine of t over 2. So notice that a curve that is defined by a position vector is really just another way of expressing a curve that is defined parametrically. And so for this reason, you guys immediately recognize that the trajectory of this curve is going to be a circle. In fact, it's going to be the circle x squared plus y squared is equal to 9, just like that. Now we want to ask the question, what is the velocity as a function of time? And so the velocity as a function of time is going to be the derivative of the x component, or negative 3/2 sine of t over 2 in the I direction, and 3/2 cosine of t over 2 in the j direction. If we draw for ourselves the trajectory, here's our parametrically defined curve, like so. And at any point, my position vector is going to be a position vector here, like this. And r of t is equal to 3 cosine t over 2i plus 3 sine t over 2j. Here's the thing that I want you to observe about the position vector and our particular velocity vector. Our velocity vector is guaranteed to be tangent to the circle, and there it is. And I want you to observe that the slope of that velocity vector, which would be the y over the x, can be written like this. dy dx, the slope of the curve at that point, is equal to dy dt over dx dt, a familiar result from our parametric curves here. And dy dt is sitting right here in the velocity vector. That's dy dt. 3/2 cosine of t over 2. And dx dt is sitting right here in the velocity vector, negative 3/2 sine of t over 2. And various things cancel out, giving me negative cosine over sine, or negative cotangent of t over 2. Meanwhile, I want you to observe that the slope of the r vector right here is going to be 3 sine of t over 2 divided by 3 cosine of t over 2, which is equal to tangent of t over 2. And look at what we've got. The slope of the r vector and the slope of the velocity vector are negative reciprocals of each other, so that the velocity is perpendicular to the radius at every point along the curve. And if you know any geometry at all, you're not surprised by that fact. Tomorrow, when we do dot products, we'll have an easier and more elegant way to show the same thing. We'll show that the dot product of our velocity and position vectors is identically 0 for an object moving along a circle. So the key point here that I want you to see is that it's very easy to compute the velocity vector, and it gives us a satisfying result. Well, if differentiating once works easily, differentiating twice should work easily also. And so we're going to define our acceleration vector as simply the derivative of the velocity vector. Or in other words, it's going to be the second derivative of the position with respect to time. Graphically, the acceleration is a little bit trickier than the velocity. You remember that when we did motion along a straight line, that the acceleration was a little trickier than the velocity. If I have my object moving along a curve with initial position here and final position here, and I go to any point along that curve, the velocity vector is going to be tangent to the curve. The acceleration vector will not, in general, be tangent to the curve. Instead, the acceleration vector is going to point in some way like this. And the only things that we can say about the acceleration vector at this time are this. First of all, that the acceleration vector is going to have a component that is going to be inwards along the curvature of that curve. See how my curve is curving like that? The acceleration vector is going to point inwards towards the center of an imaginary circle that is tangent to the curve, badly drawn here. And it will also possibly have a component that is parallel to the velocity, like that, and that component parallel to the velocity is going to tell us whether or not the object is speeding up or slowing down. If the acceleration is pointing forward in the direction of the velocity, the object will be speeding up. If it's pointing backwards, the object will be slowing down. And tomorrow, when we do our dot products, I'll actually prove that. For now, I just want to give you an intuitive picture of what's going on. The key is that the acceleration does not usually point in the direction of the. Furthermore, you remember that when we did motion along the line, we had a simple rule for speeding up, slowing down. We said that if the acceleration and velocity were in the same direction, then the object was speeding up, and if they were in opposite directions, then the object was slowing down. That rule no longer has any meaning, because the velocity and the acceleration have an infinite number of possible directions between them. So we're going to have to modify that tomorrow. There's a little bit more that I want to say about the calculus of vector value functions, and that is this, that such things as the mean value theorem and Raleigh's theorem and all of our theorems about if f prime is positive, then f is increasing, and if f prime is negative, then f is decreasing, and so on and so forth. Etc. All those theorems that we learned in Chapter 4, unfortunately, these are not going to apply to vector value functions. And the reason is fairly simple. The reason is fairly simple, and that is that all of them really come down to being able to connect local extrema to critical points. And for a vector valued function, there is no such thing as a maximum or minimum value, because I'm working in 2 dimensions. What would it mean to say that this point is greater than that point? Well, in the x sense or in the y sense, or what? You see? So there is no self-consistent way to compare points, and because there is no self-consistent way to compare points, all of the theorems that we that dealt with increasing and decreasing and so on and so forth are no longer of interest. We will be able to say some things about curves. We're going to develop that over the next couple of days, but we're not going to be able to say that, for example, that there is a time at which the average rate of change equals the instantaneous rate of change. And to help cement that, I want to go back to our circle and just observe a simple counterexample. Suppose I wanted to try to come up with a mean value theorem-like theorem. If I take one trip around the circle, all the way from here, all the way back to here, then my average rate of change is 0. Because my final minus initial positions is 0. But there is no time at which my instantaneous velocity is equal to 0. The object never stops moving. So with that simple counterexample in mind, just sort of put the idea of mean value theorem out of your head. But let's do something here. You remember that we defined speed as the absolute value of velocity in one dimension. Here we can extend the notation to say that the speed is going to be the magnitude of the velocity vector. And that magnitude can be written like this. It's going to be the square root of vx squared plus vy squared, using the Pythagorean theorem. But notice that the velocity component in the x direction is just dx dt. And the velocity component in the y direction is just dy dt. So that we have this expression here for our speed, which is telling us how quickly the object is moving without regard to direction. The speed has several fascinating properties, but here is the one that I want to bring out at this time. If we come back to the circle as our example here, and if we compute the speed, remember that our circle's velocity was negative 3/2 sine t over 2 in the I direction, and 3/2 cosine t over 2 in the j direction. Then the speed for this particular circle is going to be the square root of negative 3/2 sine t over 2 squared plus, clearly out of room there. Okay. Plus 3/2 cosine squared, or 3/2 cosine t over 2 quantity squared. And if we now simplify this, something magical happens. I have a common factor of 3/2 squared underneath the radical, which I can factor out as 3/2, and I end up with sine squared plus cosine squared is equal to 1. So that for this object moving around the circle here, I'm actually moving at a constant speed, even though my velocity is now a constant vector. So this is something that is very different from our motion along a line, and that is that speed can be constant even if velocity is not. Very, very interesting. There's more that we can say. Let's, for example, ask this question. Can I find the distance that is traveled by the object from 0 to t? So our goal here is to compute the distance traveled from 0 to time t. Let's do this generally for a curve here. And if this is t equals 0 right here, this is t equals t final right here. What I want to do is to compute distance. You remember that we did this before, and we did it by approximating our curve with line segments. Like that? Not Euler's method. You know, that was a differential equation solution method. Although there is a connection to that, right? So we did approximate a solution curve with line segments with Euler's method. Yes, but here what I had in mind was finding the length of the curve, and we did that by taking the curve and breaking it up into segments delta s or delta s sub I, and each delta s sub I was equal to the square root of delta x squared plus delta y squared. Remember that? And then we factored out delta x or delta y as appropriate, and we ended up with an approximation for each of our line segments that look like this. You remember that? And then in the limiting case, we said that s was therefore the limit as the size of our delta went to 0 of the sum of the delta s's, which then became the integral from a to b of root 1 plus dy dx squared dx. Remember that? Yep. Well, we're going to do the same procedure, but instead of factoring out a delta x here, we're going to observe this, that if I take my curve and approximate it with these line segments delta s, I can think of each one of them really as a displacement vector. And each one of those displacement vectors takes me from one position to another straight across the curve, like so. And the magnitude or length of each displacement vector is going to be delta x squared plus the square root of delta x squared plus delta y squared. So where are we going to go with this? Since each one of these is a displacement vector, then what I can do is to write for each delta s sub I can write the magnitude of that delta s sub I as the average velocity times delta t sub I. So that the magnitude of the delta s is going to be equal to the magnitude of the average velocity times the absolute value of a positive quantity delta t sub I. In other words, it's going to be equal to delta x over delta t squared plus delta y over delta t squared times delta t for each one of these. And if I now take the limit as the size of delta t goes to 0 of the sum of all of my delta s's, then what I get is the integral from 0 to t of, look at that, dx dt, the square root of dx dt squared plus dy dt squared dt. Well, we approached all of this from the perspective of finding arc length or distance along the curve. But now take a look at the quantity that is our integrand. What is that? It is the speed of the object. It is the magnitude of its velocity vector. So that we now have an extremely elegant result that imitates what we did for motion along the line in one direction. And that is that the distance traveled for arc length is simply the integral of the speed. Oh, we've done that before. And furthermore, if I appeal to, let's call this distance d, if I appeal to the fundamental theorem, I find that the derivative of d with respect to t is the derivative with respect to t of the velocity, which gives me, which is equal to the velocity at any time t. In other words, not the velocity, the speed, the magnitude of the velocity of the speed. In other words, the speed is the rate at which the distance is changing as the particle moves along the curve. So if I have some crazy curve like this, and I'm going from this point to this point in this direction, then at any point in time, the speed tells me how quickly I am making progress along the curve. How quickly am I moving along the curve in this direction? Now think about the speedometer on your car as you drive along the curvy road. That speedometer is telling you how quickly you are making progress along the road, how quickly your distance is changing along the road. Does that make sense? Well, let's take all of this and put it back in the context of the circle. And I want to review what we did with our circle. We started with a circle defined in terms of three cosine t over 2i plus 3 sine t over 2j. And we found the velocity vector by differentiating term at a time. Go ahead.
3 negative 3 sine over 2 sine t over 2 pi plus 3 over 2 cosine sine over 2j.
Good. And we also found the speed, and when we found the speed, we found something sort of magical, and that was that it was the square root of this squared plus that squared. Which gave us speed actually, but it gave us what value?
One? Need one?
Think carefully.
Oh, 9/4. Which is 3/2.
3/2. Square root of 9/4, which is 3/2. In other words, for this particular path, the object is moving with a constant speed. Now, just to close the circle, so to speak, let's find the acceleration of our object. And the acceleration, of course, is going to be the derivative here. So what do I get for the acceleration?
Need 2 cosine, 4. Cosine 2i plus 3/4. Oh, it's negative.
Good.
Cosine 2/4. Sine 2/2j. I'm sorry.
It's okay. Do you notice anything interesting about your r, your position, velocity, acceleration vectors?
It's half.
The coefficients here, yes, each are half, and that's because of your t/2, yes. Good. Anything else?
The sine.
Plus or minus sign?
Yeah.
Can you write the acceleration in terms of the position vector?
Oh. Negative 1/4r.
Yes. Very, very, very interesting. This does not always happen, but it does happen in the case where an object is moving along a circle with constant speed. And in physics, we call this constant circular motion. And it's a very famous model for objects as they move around things. Notice that we pointed out earlier that the velocity and the position vectors are perpendicular to one another. For constant circular motion, the position and the acceleration vectors are going to be in opposite directions. So that the acceleration is a special kind of acceleration that we call center-seeking or centripetal acceleration. And this came about because we began with a position function that represented motion around the circle with a constant speed. Let's say a little bit more here, and then the bell is going to ring. Since we have our speed, if I want to find the distance traveled at any time t, then that distance traveled at any time t is going to be the integral of the speed. But because my speed is constant, therefore I get an elegant result, which is the distance traveled, which is 3.5 c, no matter what. So let's go a little bit further with this. If I want to go all the way around the circle, starting here and coming back to my original point, then to do that, I'm going to have to go one trip around. Notice that that means that t/2 is going to have to be equal to 2 pi in order to get me all the way back around, so that I've got to travel from t = 0 to t = 4 pi to get one trip around the circle. That means that the distance that I will have traveled once I go all the way around the circle is going to be equal to 6 pi, which is 2 pi times the radius of the circle, the circumference of the circle. And so everything fits together. It's really nice. What we're going to do tomorrow is that we're going to talk about how to take two vectors and find their scalar product or dot product. And that's going to allow us to find the projection of one vector into the direction of another. And that's going to allow us to say a lot more about our acceleration. But at this time, you actually know everything that you need to know to analyze motion, to analyze motion for the APA exam. You need to be able to find, just to summarize everything here, you need to be able to find given a parametrically defined curve that's expressed in terms of vectors, you need to be able to find velocity vectors. Acceleration vectors. You need to be able to find speed. And you need to be able to find distance traveled, which is going to be the integral from the first time to the last time of speed dt. And that's really it. It's very simple. The reason, by the way, that I wrote these in terms of with the Euler notation x prime instead of the dx dt as I did previously is to help you see that those are interchangeable pieces of notation. Questions?
For the previous slide, just a small question.
Yeah.
The b or pi, is it 2 times the circumference?
If I go one trip around the circle geometrically, I should get one circumference. If I go one trip around the circle, then my final angle here has to be 2 pi. And since the argument is t over 2, that means that t over 2 would have to be equal to 2 pi. So it takes me 4 pi seconds to get from the starting position all the way back around to the final position.
But like r was 3 over 2.
R was 3 times cosine of t over 2.
Oh, yeah.